This week we are doing the nitrogen cycle, so moving on to another one of our chemical cycles. So just before we begin, probably a lot of you noticed the emails that are doing the rounds. I have been trying to clarify certain issues as regards to the assessment, where certain things aren't clear to people. Just like to remind you though that the deadline for submission is tomorrow night. And after that, the standard late penalties will apply unless you already have permission to submit late. And then I won't be accepting any submissions at all a week later, and I should hopefully have the marks and feedback released a week after that. Also, the second assessment, which is in the form of an open book online quiz, that is going to get released next week, but you've got a very long time scale to do that one. That's because of basically when Easter and fieldwork falls this year. Okay, so nitrogen cycle. Today's intended learning outcomes are kind of similar to the sulfur cycle one, so we'll be identifying the major forms of nitrogen within the Earth system. We're discussing the processes, with a particular focus on the chemical and the biological processes, and how this changes the forms of nitrogen within the Earth system. And then we're also going to talk about the anthropogenic impact to the nitrogen cycle. So we're going to be dealing with the causes of the perturbations, the budgets, and dealing with which Earth system compartments are affected. Right, so back onto the periodic table. Right, so for those that already have a copy of the PowerPoint, please don't look ahead. Can anyone give me any forms of nitrogen that you might expect that are relevant to the Earth system? Yeah? Nitrogen dioxide, yeah, that's a common pollutant, yeah. Elemental nitrogen, absolutely. There's a lot of it in this room. Yeah. Nitric acid, yes. Amino acids, good. That's a biological form. Yeah, any others? There's first one got mentioned, elemental nitrogen. So, yeah, that's the most common form of nitrogen on the planet. It makes up the majority of the atmosphere, and it's a very stable form of nitrogen. Most of the time considered inert, and the reason it's considered inert is because it's got this triple bond between the two nitrogen atoms, and that's an incredibly strong bond. It's very difficult to break. It does get broken, but it normally has to be, in order to overcome that bond strength, you normally need a catalyst or something, or some kind, or be it a biological catalyst in the form of an enzyme or an inorganic catalyst. We'll get onto that in a sec. Also, it's also worth noting that when this bond is remade, it releases a lot of energy. So you'll find that a lot of explosives have nitrogen in them. So examples I gave there is TNT, nitroglycerine. Whenever you remake this bond, it releases a lot of energy. But of course, once you have broken this bond, you can then go on to make loads of other things out of nitrogen, and it becomes a lot more, generally it becomes a lot more reactive once this bond's broken. And part of the effort of getting nitrogen active in the Earth system is converting it into another form in the first place, so it's then available for any other chemical or biological processes. And these other forms we collectively refer to as reactive nitrogens, or NR. And then these are the kind of major forms, notwithstanding the biological forms. Again, I'm not going to give a grand tour of this. You'll notice most of these are different forms of oxides of nitrogen. So we've got our oxidation state, as with sulfur, can exist on a full range. This time it's +5 to -3. So we have all these oxides of nitrogen. Most of these are fairly chemically reactive. The one exception is nitrous oxide. This one's relatively inert as well. We'll get onto that in a bit. And then finally we've got the reduced forms of nitrogen here. So we have ammonia, ammonium, and also urea as well. So, and then moving on to our, the amino acids. nitrogen is a very vital component of biology, and that comes from, at its most basic, is this functional group here, the amine. So you've got R, which is an organic molecule, can be lots of different things, but we have a reduced nitrogen group attached to it. And then what you can do is you can react this with a carboxylic acid to make an amide. So this forms the basis of a lot of biological polymerization occurring, like forming bigger and bigger molecules. And then what you have is the amino acid, which is basically where you have an amine and a carboxylic acid together. So this forms one of the main building blocks of life, where you have your R group here, which can be any kind of specialist organic molecule. You've got your carbons here in the middle, but then these carboxylic acid groups and the amine groups, they're the bits that can then join together, so you can start sticking all these amino acids together and make bigger and bigger organic molecules, and then this forms the basis of how you form proteins and so on. And so it's no stretch to say that nitrogen is every bit as biologically vital as, say, carbon. But if the biosphere is to make use of this, it's got to be in a form that's available. Now, the overwhelming majority of complex organisms cannot use nitrogen in its elemental form. Breaking this bond is just too difficult, basically. So what we talk about is nitrogen fixation. Now what this really means is just converting nitrogen into one of its reactive forms. Plants and other producers, they can utilize nitrogen in its reduced state. So things like ammonium, that it takes up into the plant and then it can form amides. Then from forming amides can start forming carboxylic acids and so on. Plants can also use nitrate as well, but what has to happen there is it's got to go through an extra step of converting the nitrate into a reduced form. So it takes a little more effort. But then this is so if you have some reactive nitrogen, this is how you get it in the biosphere. Now, of course, this is going off the model of talking about our producers, consumers, and decomposers. All of this heavy lifting is being done by the producers, so much similar with other processes as well. Consumers, so animals such as ourselves, we don't do any nitrate assimilation. We get all our protein by consuming other organisms, so other plants and animals. That's how we get our nitrogen. But then there's other transfers within the biosphere and temporarily in and out of the biosphere. Urea, that is one of the main components of urine. That's a byproduct of metabolized protein, so that's kind of like the leftover bits of nitrogen that are coming out of used protein, so to speak. But that can then be reused by plants and decomposers and so on. So you've got this reduced nitrogen, you're keeping it as reduced nitrogen, and then it can then be taken back up into the biosphere very easily. What this means is that once you have this reactive nitrogen in the biosphere, then it will be kind of freely passed around quite a lot, be it through consumption, decomposition, or reassimilation of the decomposed products. So just to make that final point, the majority of global nitrogen fluxes, they're between organisms or either going from a reservoir into the biosphere or out of the biosphere. So this is just a kind of quick overview of the type of thing we're talking about. I'm going to be talking about the gaseous losses in a second, but this is just this cycle here where we have our organics. Now, so this is our biosphere. Plants take up nitrate, animals eat plants, but then eventually it gets discharged as urea, where it's remineralized to ammonium, and then that can get converted back to nitrates. More on that in a second. But then that can still go, and that can go right back into the biosphere again. And then there are ways out of this. So there's the leaching, so that is transport out through being dissolved and going into groundwater. And we can also have denitrification, which I'll get onto in a second. But in order to get that far, we've got to go through the first step, which is calling here fixation. Now, this is kind of like a term used from agriculture where we talk about nitrogen fixation. But what we really mean is just basically getting elemental nitrogen into a reactive form that can then be utilised and reutilised by the biosphere. And one of the natural processes that is responsible for this is through some bacteria and algae. They basically have the ability to, using biological enzymes, to break this nitrogen bond and get it into a form that they can use. This is a very high energy reaction, so needs to be done in the absence of oxygen. If there's any oxygen present, then that will just kind of completely wreck everything. So this is mainly an anaerobic process. As a result, these organisms kind of favour certain types of environment. Now, those who are familiar with biological nitrogen fixation in agriculture will know about the leguminous plants. What these are plants that have a special adaptation, which they provide a favourable environment in their root structures for these organisms, and they exist with them symbiotically. So the deal is that these microbes, they get a favourable environment, they get kept away from all this harsh oxygen and everything like that, and in exchange they provide this nitrogen fixation for the plants. There are other types of nitrogen fixers as well. There's free-living ones, so within the water, within soils and so on. They can also do some nitrogen fixation. They're not quite as efficient. And there's also other adaptations as well, whereby plants, even if they don't incorporate them into the roots, they will still kind of create a favourable environment for them in the local soil as well. I also highlight cyanobacteria. That's one of the important ones in aquatic environments. Not necessarily as efficient as the ones in soils though. And then the final point there, and I'm going to come on to this, the traditional farming methods. So if you're going to rely on biological nitrogen fixation, the traditional way of doing this would be through techniques such as crop rotation, or if going even further back, practices such as slash and burn and things. Also manuring as well. So animal manure will contain a lot of nitrate as well. But I'll get on to that in a bit. Okay, so this is an example of the root nodules that you get on a leguminous plant. So this is just an example of a clover root, and then you can see these root nodules here. These basically these nodules on the root, these house the bacterial colonies that do the nitrogen fixation and are beneficial to the clover. And this is just one example photographed on the... I mean, this lawn doesn't exist anymore. It's got a flipping construction site on top of it. But this was just photographed at a particular time of year on one of the patches of grass outside. One of the things you'll notice is that the grass here isn't doing quite so well. But we've got all this clover here. Now, one may speculate that part of the reason is if the grass is currently finding itself nutrient limited, particularly for nitrogen, but the clover isn't. That is one such situation where one of these adapted organisms can actually prosper when one of the other organisms which doesn't have this facility isn't. Well, that's not the only biological process that can convert forms of nitrogen. Another one is nitrification. So there's other types of organisms that can oxidize ammonium into oxides of nitrogen and ultimately nitrate. This is similar to the sulfur. This is part of the metabolism, gains energy from it. So it's it requires the presence of oxygen. So this is where you have like aerobic soils and things like this. But what can happen is you take all this ammonia, convert it to nitrate, and as we'll get onto in a bit, this can cause soil acidification, because what you're doing is you're changing something alkaline into something acidic. And then, but that also changes the properties as well. You can change how it adheres to the soil, and it also changes whether it can get leached out the soil or not. And then it can also go on to affect riverbeds and so on, the groundwaters and rivers and so on. And then finally, there's yet another type of organism can actually convert back into elemental nitrogen, and this is called denitrification. So we're starting out with our nitrate here, and then reducing it back to nitrogen, and then this again is a source of energy, what I was saying about earlier, so getting it back to the nitrogen form. So this is the way of closing the loop when it comes to converting things back to nitrogen. So starting out at nitrate, going through nitrite, nitrous oxide, nitric oxide, nitrous oxide, and then finally nitrogen. But this whole chain of reactions isn't perfect, and all these various intermediate steps, these are produced as kind of like a byproduct. And as I say, this is how you close the loop. But then if we were to draw this kind of biological loop here, so we're starting out with our nitrogen here, and then we go through the nitrification and denitrification process, fixation first, sorry. We start producing these byproducts here. And this is kind of like referred to as the leaky pipe model. So if we're feeding nitrogen around this model here, and we're going through all these different stages of these biological processes, then the more and more we go around this kind of cycle, the more and more nitric oxide and nitrous oxide we start producing as a byproduct. So this kind of principle is if we increase all this biological activity involving nitrogen, be it deliberately, through fertilization, say, or even if it's accidental, the more of this activity we create, then the more of these oxides of nitrogen byproducts that we also create in the process. So this is one of these. This is one of these kind of unintended consequence processes that you can get when the biosphere is stimulated. So before I go on to the human perturbations, there's a few other natural processes that need to talk about. So we have the ammonification process. This is when you take something like byproducts like urea, or also dead tissue as well, and then converting that back into ammonia. And ammonia this is primarily the role of the decomposers. Once it's converted to urea, it becomes very available for the biosphere, but it also can be released in the form of a gas as well. One of the big ones that's associated with agriculture is what happens when feces comes into contact with urine. So urine's a liquid, but when it comes into containing urea, feces, on the other hand, contains a lot of anaerobic bacteria, which include the ones that will take part in the ammonification process. As a result, when the two mix together, you very rapidly get a lot of ammonia forming, which can exist in the form of a gas. Reason that's important is intensive farming promotes this process. So if you just have a load of cows in the middle of a field, minding their own business, the urine and the feces are not necessarily going to come into contact with each other very readily. But if you have all these cows cooped up in a small paddock or in a shed, then there's a very good chance they'll come into contact with each other, and you will produce a lot of ammonium. That's not necessarily a bad thing, because a lot of farming practices involving making a slurry from the urine and the feces. They let it react for a while, it builds up the amount of available nitrogen content, and then they can spread it on the fields to use as a fertilizer. Another natural process, completely inorganic one, is it does exist as a mineral. Not nearly as important as, say, the sulfur minerals, but there are certain nitrate reservoirs in the lithosphere. Examples I've given here are the different forms of saltpeter, so potassium nitrate, sodium nitrate. One of the things about these, though, is that they are these minerals are very soluble. So if they're ever exposed to the surface, and unless you're in a very arid condition, then they'll very quickly be weathered by the rain. So, okay, so those are the kind of natural processes. To summarise, but also to do one of the kind of favourite activities of this module, is we're going to draw a diagram and identify our reservoirs. And so for this one, it's a fairly simple diagram here. We've just divided it into atmosphere. I've bunched the hydrosphere, pedosphere and atmosphere together, and the hydrosphere and pedosphere for the reduced forms of nitrogen, then the hydrosphere and the pedosphere for the oxidized forms of nitrogen, and then at the bottom we've got the biosphere here. Well, then these are all the processes we were talking about. So we've got the atmosphere. I've put nitrogen and nitrous oxide here. So that leaves the atmosphere through fixation, and then going into the hydrosphere, pedosphere and atmosphere, and then through nitrification into the biosphere, and you can get all this going to and from there, and finally denitrification, which sends it back to the original pool in the atmosphere. One thing I would draw your attention to is that every single one of these fluxes is controlled by a biological process, as I've identified them here. So this is just reiterating the point about how much biology has to do with the nitrogen cycle. Okay, so that's the kind of basics of the natural processes, and I've kind of hinted at the role that human activity might have in perturbing this. So this is just going to be doing a quick history of reactive nitrogen in the Earth system. Now, much like with the carbon cycle, we kind of use as a baseline the pre-industrial period. It's not entirely in sync with the carbon cycle industrialization. The big event for the carbon cycle was when the use of coal became widespread. It's ever so slightly different with nitrogen when the point at which it picked up was. But talking about our pre-industrial period here, so starting about 1850, the agricultural revolution was still in full swing at this point. So people were beginning to understand how things like crop yields and nitrogen worked and things like that. But what was going on is the amount that was of nitrogen, the amount of reactive nitrogen that was created, the amount that fixed, was staying more or less constant through the latter half of the 19th century. So this is the cultivation line here. So this is the amount of reactive nitrogen. This is also the world's population here. And then as people were beginning to understand this more, noticing the world, if the world's population was increasing, the number of mouths needed to feed were going up, but it was realized that if you're going to sustain the world's population, you'll need to grow more crops, and that will require more nitrogen to get fixed. But if you're only fixing so much nitrogen per year, would you ever be able to grow enough crops to feed a hungry population? And cometh the need. The kind of big development that occurred was actually here in the early 20th century. This is the invention of the Haber-Bosch process. Now, I don't know how many of you are familiar with this. The Haber-Bosch process is generally regarded to be one of the most significant processes ever developed in chemical engineering as regards the history of humanity. But ironically enough, sustaining the world's population was not the original motivation for developing the Haber-Bosch process. Actually came in 1908, patented in 1908. This was just when people were just developing chemical processes, and it got patented by Fritz Haber. But then a few years later, Germany found it really useful when World War I started. As I was saying, nitrate is used in a lot of explosives, and at the time, the kind of feedstock for making these was the Chilean saltpeter that I was talking about earlier. So this is a form of mineral nitrate. So if you want to make explosives, you needed a lot of it. So that was what they were using. But their supply of saltpeter got cut off at the start of the First World War. So they needed somewhere else to get their nitrate, and then turns out this process, Fritz Haber, he made other developments for the German war machine during the First World War. He had this process which could then supply as much nitrate as they needed to be able to make their munitions. So the Haber-Bosch process looks really simple. All you're doing is you're taking nitrogen and hydrogen and making ammonia. The really complicated bit was what he had to develop was the exact conditions in order to promote this reaction. So finding the optimum temperature, the optimum pressure, and also the right catalyst to use. And the one he developed was basically using a high pressure, high temperature in the presence of an iron catalyst. And then this allows this process to go ahead. And then, but of course, once it's reactive, then converting it into another form is dead easy. So then enter the Ostwald process. It's another chemical process, which is then to just take this ammonia and then oxidize it in stages until you get nitrate. Wasn't really used as a fertilizer at that point. You have to actually go forward in time a few decades to after the Second World War, when people started adopting it as a way of making reactive nitrogen as a fertilizer. But of course, this is the object of nitrogen fixation is to get your nitrogen into a nice, convenient reactive form, and then from there on you can do all kinds of things with it. So in the modern world, you're making this ammonia and this nitrate, and then from there you can make fertilizers such as ammonium nitrate, ammonium sulfate, potassium nitrate, so on. You don't have to use the salts either, I should say. You can inject ammonia directly into soils if you want. It's generally not preferred because it tends to just come out as a gas rather than kind of bind to the soil, but if it's acidic you can do that. So, this is what our graph now looks like. So we had our development of the Haber-Bosch process here in the very early 19th century, but then after the end of the Second World War, and then particularly during the 60s and 70s, really began to increase. And that's also in line with a major population increase that occurred after the Second World War. That is not coincidence. If you look at the amount of nitrogen fixation through cultivation, it's gone up a bit, but nowhere near as much. The majority of the nitrogen fixation occurring in the world is actually through this Haber-Bosch process. And this has allowed the world's population to increase over the 20th century. And also there is some other artificial nitrogen fixation, which I will talk about. It's not for food production, but there's also nitrogen fixation that's formed through other processes as well. Not the majority, but they also add to the amount of reactive nitrogen being produced. So we're fixing all this nitrogen. So in theory, if all we were doing was taking all this fixed nitrogen, using it to grow crops, and then doing whatever with the crops, that would you'd think, well, what's the problem? But there's a few kind of side effects to over fertilizing land, as I was saying earlier. First of all, ammonia. Ammonia is naturally a gas. Okay. Now, if you over fertilize some land, increase the amount of ammonia that's available, that can then just disappear back into the gas phase, into the atmosphere, and then go off and do something. But it's also true of intensive animal farming, as I said. That causes a huge amount of excess ammonia to be released. Also, the leaky pipe model. If we over-fertilise some land, the more and more we stimulate the nitrogen cycle in soils, the more and more nitric oxide and nitrous oxide we create as a byproduct. Now, the nitrous oxide is important. I'm not going to talk too much about nitrous oxide. It's a fairly inert gas, and it persists for a long time in the atmosphere. Reason people care about this is because it's a greenhouse gas, and I'll get onto a slide on that in a second. It's not as significant as carbon dioxide, but it's still a contributor to the greenhouse effect. Furthermore, because it's a long-lived gas, it can also get into the stratosphere and potentially perturb the ozone cycle in the stratosphere too. And then also the final one which I'd highlight, and this one perhaps isn't a negative one, which is, as stressed in the carbon cycle, if we promote the activity of the biosphere through fertilisation, then in theory that can mean we sequester more carbon. So we take more carbon out of the Earth system. Although, as I stressed in the carbon cycle lecture, you then got to worry about what you do with the carbon afterwards. If you grow some crops and then eat the crops, then ultimately the carbon ends up back as carbon dioxide through respiration. So here's our nitrogen dioxide trends. Nitrous oxide trends. This is again showing a very simplified diagram of how much the anthropogenic nitrogen fixation has been occurring on top of the background. So we've got fossil fuel combustion, legume crops and green manure, so that's our biological nitrogen fixation through cultivation, synthetic nitrogen fertilizer. Then we also have these natural sources, lightning and the natural biological fixation. So that's the non-man-made nitrogen fixation. And then this is a graph taken from the IPCC report. This is our nitrous oxide over time. You will notice it bears a very strong resemblance to the similar graphs for carbon dioxide and methane, where we get this big increase starting around about the year 1900. And what you can see here is it really starts to pick up pace in the second half of the 20th century. That again is just completely consistent with the increased use of nitrogen fertilisation, increasing the amount of soil activity, increasing the amount of nitrous oxide being released as a byproduct. So this is just to summarise, in case anyone's wondering what the picture is. That's taken from one of the papers that I cited here. The link should be on Blackboard. If it's not, I'll enable it as soon as I finish. But what this is an illustration from the Coleridge poem, The Rime of the Ancient Mariner. That's the origin of the phrase, water, water everywhere, but not a drop to drink. It's a similar thing with nitrogen. There is nitrogen everywhere. But most of it is unavailable to the biosphere. So what we care about when we're talking about the nitrogen cycle is this reactive nitrogen. So to summarise, biologically vital, there are these natural processes that fix it, but these human activities, mainly the Haber-Bosch process, but also the fossil fuel combustion and cultivation fixation, that has been a huge addition to the nitrogen cycle. So, now that's quite an early break. However, I would still like to just stick to the 10 minutes because the second half of this is, I don't know if anyone's looked ahead or not, but I'll warn you, the second half has got a certain amount of chemistry to it. So, are there any questions at this stage? Right, I'm going to propose we have the break early, because as I say, the second half we cover quite a lot of chemistry stuff, and I like to take that at a leisurely pace if possible. So if we could come back here at 1:45, is that all right? Yep. Okay, those of you who haven't used this, where's the scanner located? Is that, how far around did that get? Okay. Those of you who haven't used the scanner yet here, please do so.
You know, for a report,
Yeah.
How are we meant to hand it in? Are we meant to write our name on it? Are we not?
Right, your submission is through Turnitin,
Yeah.
so it automatically gets attached to your. What will happen is that when you put it in the Turnitin, I'll mark that manuscript, and that mark will be attached to your login.
Okay, so but as in like on the actual document, do you want us to write our student number or our name?
It doesn't matter.
Okay.
I mean, well, okay. It would help just in the sense that if something goes wrong, then I'll notice it. So it would help to put your name and your student number on just to kind of idiot check it. Do you know what I mean? I'm not saying I don't trust the system, but we've had occasional glitches in the past. That's all.
Okay.
But if everything works the way it's supposed to, you don't need to worry about that. Your mark will be attached to your login on Blackboard.
Okay, thank you.
All right. Oh. Oh, thanks.
It's tomorrow at midnight submission.
11:59
p.m.
11:59 p.m. Yes. Be very specific because I've had to impose late penalties on people submitting 2 minutes late. Some people really do leave up to the last minute, and I would not recommend.
No, to be honest, I don't plan on it. But
yeah.
I'm planning on getting it done tonight.
All I'm saying, don't leave it to the last minute.
Oh yeah, absolutely.
I routinely, every time I set an assignment, I routinely get lots of emails saying I submitted. I had a problem with the website. I submitted 5 minutes late. Am I still going to get hit with the late penalties? Unfortunately, I've got to draw a line somewhere, so do not leave it to the last minute. Yep.
I want to ask, in this system, the drive deposition is gravity.
Gravity or where's the system? Right. If the particles are larger than about micron, they will settle through gravity. But the smaller particles, so because it's smaller than micron, then they don't fall very fast, so they're not readily lost through dry deposition. That's what it's saying. But it is principally gravity for dry deposition. But the smaller particles are not lost very easily through gravity.
What does that mean? If you choose the particles?
Well, if there's not many particles present, I mean, if you go to this slide here, if you imagine that you have these particles present, if there's a sulfuric acid molecule trying to condense on something, it has to actually come into contact with another particle to condense onto it. If there aren't many particles present, then it's got nothing to condense onto. It can't condense fast enough. So what will happen instead is it will nucleate.
It's not.
Well, the nucleation is when, but the thing is, once you have got nucleation, then sulfuric acid has got something to condense onto. So that's when you start getting the condensation. Yeah?
There is
Yeah.
If it is lost, then it's nucleation.
Yeah. So if there's not enough particles, but you are producing sulfuric acid, yeah, then the sulfuric acid will nucleate. But once you have lots of particles present, then it will condense onto the particles instead. Yeah? So when you do, so if you see this example here, so there's not many particles here, so you get nucleation here. But now that you have all of these particles, all the sulfuric acid is instead condensing onto these. So there's no nucleation here. All the nucleation occurs here. Does that make sense?
The red means there's more
Yes, the red means there are more particles.
particles.
Yeah, this is time, and this is the size of particle. So this is where the nucleation occurs. Yeah, and then what happens is you get the nucleation here, that's where they start forming new particles, and then as they get bigger, that's when you start getting condensation, and they start just getting bigger and bigger and bigger.
By the way, the larger atmospheric particles optically thicker haze means lighter and negative.
Yeah. So when you get a haze, yeah, so when you get a haze forming,
Why? I remember that there are smaller particles
right, well no, if you have more particles, that will increase your albedo. If you have larger particles, that will albedo. Now, that's actually quite a good question though. For a cloud, the difference is when you have a cloud, you have a certain amount of liquid water, yeah? With the hazes, the mass is the particulate matter that you're adding more and more mass. For a given cloud, you have a fixed amount of water. So the albedo goes up when you have the same water content but on more particles. For a haze, you have the same number to get a thicker haze, you have the same number of particles but more particulate matter. I don't know if does that make sense? Yeah. That's a good point though. I've not thought about it that way though. Yeah. Is it the same? That's the question.
The value is the same.
Is it the same? Is the question. Consistent with means not necessarily equal to, but is it?
So this the time means when it's the change of the burden become 60%.
All I'll say, right now, I see. This is the thing. This is one of these situations where, if I was to say yes or no, that would be helping you get the answer. Okay, but all I will say is the question is it consistent with the turnover time? And this time, all I'll say is refer to the lectures. Okay.
Yes.
So when we talk about the time taken when we talk about reaching equilibrium, okay. I'm not going to tell you whether you got the answer right or not. Sorry. No.
I tried, but
The question is it consistent? That's the question. I'm not going to tell you the right answer. Come on.
okay.
I'll tell you the question, which is it consistent?
For 2.3 with the marine, changing the marine MPP, is the question asking us to compare? It refers to a perturbation and us, how it changes relative to the perturbation. Is the perturbation changing the marine MPP to the limited? So is it asking to compare the model before and after changing the marine MPP, or before and after the 1.5 perturbation in this new system with limited marine MPP?
the spirit of the question is, what difference does making it limited do? How you answer that is up to you.
Okay, that clarifies it. Thank you very much.
Yeah. Okay, can we start again soon? Huh?
For each of the questions, do I need to graphs to show?
The brief does say that for the questions you should be producing graphs as part of your answer. Well, if you don't think it needs a graph, then don't give a graph. If you think...
The graph does not
Huh?
The graph is
it depends how well you answer the questions, but the brief says that for answering most of the questions you will need a graph. Okay? Now, use your judgment as to whether you think you need to use a graphic. Okay? Okay, we need to get started again now. Okay. Okay, so if we can make a start. Right, okay, so the main theme of the second part of this lecture is going to be the human perturbation on the nitrogen cycle. So, one of the big things that human activity can do to perturb the Earth system is burn things. And this is no exception for the nitrogen cycle. So as well as all these inorganic processes, we can also just, by increasing the amount of combustion, increase the amount of oxidized nitrogen in the system. Most combustion processes will release an amount of nitrogen oxide. This is particularly true if the fuel contains traces of nitrogen, which a lot of fuels do. So if you burn some biomass, if you burn some wood, that wood will contain amino acids and so on. These will all get converted into oxides of nitrogen in an oxidizing environment. So we produce all these oxides of nitrogen from combustion. It's mainly nitric oxide, also some nitrogen dioxide. Well, then once it's in the atmosphere, these reactive forms of oxides of nitrogen, these can kind of convert between each other. So it'll stay as a reactive oxide of nitrogen, but it can quite freely change form, as we'll get on to how it does that in a bit. But one thing you'll hear a lot referred to, particularly in air quality, is NOx. Now, by NOx, what we normally mean is the sum of nitric oxide and nitrogen dioxide. Now, we refer to this collectively simply because NOx, if we treat NOx as a reservoir, it's got a much longer lifetime than, say, nitric oxide or nitrogen dioxide would individually. And it's not just human fires, there's such a thing as natural fires as well. This picture here, that was a rainforest fire that we studied a few years ago in Brazil, but that particular one we think was caused naturally. And also lightning. That's also a source of nitric oxides. The reason that is because there's incredibly high temperatures reached in a bolt of lightning. That is enough to break the bonds in. That is enough to break the bonds in the nitrogen in the air, and then it can go on to react with the oxygen to form our oxides of nitrogen. Now, nitrogen dioxide, that was one of the ones mentioned at the start of the lecture. That's a very topical one because it's probably the biggest pollutant that we have to deal with in the UK right now. This is also very topical. I put up there the EU limits that we're currently in trouble over. Whether we're going to be subject to these limits in a couple of weeks' time remains to be seen, but I'm still putting this up for the time being. It's one of the major pollutants that we care about for air quality because it is toxic. It's damaging to health, been linked to all kinds of problems relating to breathing difficulties, cardiopulmonary disorders, also even development, cognitive development in children. And the UK is currently in breach of this in a lot of places, including Manchester. So you can see here that we are supposed to, so with nitrogen dioxide, we're supposed to keep it under 40 micrograms per cubic year, averaged over a year, or 200 micrograms per cubic metre on any 1 hour. The reason we're in breach of this is mainly because of diesel engines. Now, diesel engines are specific to the problem of NOx. The petrol engines will emit NOx as well, but the NOx emitted by petrol engines has gone down significantly over the decades. But diesel engines are worse emitters than NOx for petrol, 2 reasons. One is diesel engines run at a higher pressure, but also because diesel engines run lean as well. So there's a higher ratio of oxygen to fuel in a diesel engine compared to a petrol engine. So you have this much spare oxygen, you have all these high temperatures and pressures, a certain amount of the nitrogen present in the air in the cylinder is going to get converted to NOx. A number of things that are being done about this. So they're trying to make diesel engines cleaner, so fitting better catalytic converters to them and so on. But if anyone wants to look up Dieselgate, they can. And also there's other measures to try and maybe reduce the amount of diesel engines in the middle of cities and so on. However, they're not the only source of NOx in urban environments. There's space heating and industry, but also just generally burning fossil fuels. Coal burning is a major source of NOx as well. That tends to happen outside of the cities, in power stations and so on. And then, as promised, once it goes into the atmosphere, that's when the chemistry starts. Now, the NOx, I'm not just, in this lecture, I'm not just dealing with the NOx chemistry, but because the NOx chemistry also is there's other chemical systems that are very dependent on the NOx as well. I'll be touching on a few other different chemical cycles as well. But to start with, just to give an overview, it's the atmospheric chemistry that controls how the NOx is removed from the atmosphere. Much like sulfate, the ultimate fate is going to be if you completely oxidize it into its acid form, so in this case nitric acid or nitrate, and then it leaves the atmosphere one way or the other, be it through dry deposition or wet deposition. Nitric acid can form aerosol particles. It can also condense directly onto surfaces. Nitric acid is incredibly sticky. And it's also incredibly soluble in water. So if there's any water present, be it a cloud or a body of water, it will immediately dissolve into that. Net result, because of this chemistry, the lifetime is about on the order of hours to days. It's a little shorter than sulfate, but it's on that kind of order. The exception here is nitrous oxide, as I said earlier. Now, one of the important atmospheric processes that NOx participates in is ozone cycling. Now, we've talked about how ozone is created and destroyed in the stratosphere. The ozone in the troposphere follows a very different pattern. We don't have as much hard UV in the troposphere thanks to the stratosphere high up, but we also have a lot of other things that will react with oxygen and ozone. Now, if you just take some nitric oxide and some ozone in isolation, you get this cycle forming here. So ozone will react very quickly with nitric oxide. So basically, the nitric oxide will take one of the oxygens off ozone to form oxygen, keep it for itself, and then form nitrogen dioxide. However, nitrogen dioxide will also react with sunlight. So nitrogen dioxide has a kind of like a browny hue to it. So if you ever see a really kind of grim haze that looks a bit kind of yellowy or browny, it's the nitric oxide that's giving it that colour. That's unless you've seen desert dust, of course. So what happens there is the nitrogen dioxide, that will absorb some sunlight. Now just to recap, where I've put this here, H nu, that is used to denote a photon of the right wavelength in chemistry, for those not familiar. So that's a photon of sunlight. That will, what will happen there is that will turn it back into nitric oxide, and then this free oxygen will come off. And then this free oxygen can then react with an oxygen molecule to form ozone again. Now this M here, what that denotes is some gas molecule that doesn't participate in the reaction, but it's still important because what it does is it helps to dissipate some excess energy. If you form an ozone molecule from just oxygen atom and oxygen molecule, it releases a lot of energy, and then this energy that's released can cause the ozone molecule to just fall apart again spontaneously. So what has to happen is it has to bump into another gas molecule that then carries away this heat and stabilizes it. Most of the time, this M is actually elemental nitrogen, but it doesn't actually matter what it is, so which is why we use this M there to denote the fact that it's just dissipating energy. So the things to note about this reaction, first of all, we start with ozone and nitric oxide, we finish with ozone and nitric oxide. This reaction just keeps on going round and round and round in the presence of sunlight. So ozone being continually created and destroyed, the NO and the NO2 constantly cycling between the two forms. And what happens? This is all these are all first order reactions. What happens is they form an equilibrium, and this is known as the photostationary state. Now this equilibrium, this is kind of dictated by the rates at which these reactions occur in, also dictated by the burdens, but also dictated by exactly how many of these photons you have. So if the sunlight is strong, you will get a lot of conversion to NO, and you'll form a lot of ozone. But conversely, if you don't have any of these photons, you break this chain. So if it's completely dark, you don't get this middle reaction occurring. As a result, you get the top reaction occurring, ozone and nitric oxide reacting to form nitrogen dioxide, and then that reaction will just keep going until either the ozone or the nitric oxide is used up. And this is normal what happens at night. Generally speaking, if it's dark, you don't ever find ozone and nitric oxide coexisting. They'll just keep reacting with each other until one of them's used up. Another upshot of this thing here, this cycle, is if you were what you can do is you can also think of right, what if I was to convert all of this into as much ozone as possible? So if you were to somehow prevent the top reaction occurring, then the amount of ozone you get would be equal to the sum of the nitrogen dioxide and the ozone that you already have present. That's sometimes referred to as potential ozone. So if you ever hear that term used, potential ozone, that's what it's referring to. Or sometimes it's called OX. So that's the relationship between NOx and ozone. Then we go on to the hydroxyl radical. Now, I've touched on this a couple of times already in the carbon cycle and the sulfur cycle, but I think this is an appropriate time to talk about where this hydroxyl radical comes from. Now, this is also linked to this because it's formed through ozone. Ozone, that will absorb light as well. So if ozone receives some ultraviolet light, that can dissociate to this form here, where you produce oxygen, and then you produce another spare oxygen atom. This oxygen atom can go on to just form ozone again, so the reaction just reverses itself. But in this specific situation, this oxygen atom, it occupies this excited state. It has more energy than it would do otherwise. We call this the O singlet D, which is, that's a physical chemistry term. All it means is that some of the electrons in this oxygen atom are promoted to a higher energy state. These oxygen atoms are so energetic that these can then react with water. And water is an incredibly stable molecule normally. And what this will do is it will create two of these OH hydroxyl radicals. And each one of these can be thought of as a water molecule that is missing a hydrogen. this is one of the kind of most reactive radicals in the atmosphere, certainly one of the most ubiquitous radicals in the atmosphere, often referred to as the soap or the detergent of the atmosphere. This will react with most molecules. The things that don't react with it, so your CFCs, your COS, things like that, those are generally regarded as the exceptions to the rule. So this is what drives a lot of the processes, as I was saying, in the carbon cycle, the sulfur cycle, and as we'll see in the nitrogen cycle. And also the OH radicals, the hydroxyl radicals, these can then go on to form other oxidants in the atmosphere. So the example here is forming hydrogen peroxide, and as we saw in the sulfur cycle, hydrogen peroxide is an important oxidant when it comes to the sulfur cycle as well. So the thing I would like to stress here is how dependent, this is the kind of one of the main sources of OH in the atmosphere. This is kind of the powerhouse for a lot of the chemical reactions that we see in the atmosphere as well. And this is all kind of related to the NOx cycling between NO and NO2. And then things get really interesting when we bring VOCs into the mix. Talked about VOCs in the carbon cycle lecture, and we kind of touched on this. Now, these reactions here, I'm not going to ask you to remember every single stage of this. There's a lot of very small steps here that are very complicated. What I have done is highlighted the really important ones that certainly need to get a grasp of. The example here is I've chosen methane. This isn't perhaps the best example because, as we touched on in the carbon cycle lecture, the reaction between OH and methane is actually quite slow. The bigger the VOCs, the faster this reaction is. So rather than methane, where you can the lifetime can take place over the course of years, you can have much bigger molecules where this will take place over the course of hours or even minutes. So, but for the sake of just showing an example, a relatively simple example, so not making things too complicated, this is showing when you get your methane and OH reacting, and then that forms a methyl radical. And then you've got another very fast reaction where we've got this methyl radical will react with oxygen to form another radical, methyl peroxy. But then this is when our NO steps in. The methyl peroxy radical will react with the NO. This is another very fast reaction. And then this is much like stealing the oxygen off the ozone. This will steal the oxygen off one of these organic radicals. And then in this case, forming a methoxy radical. And then this will again react with oxygen, another fast reaction, to form a peroxy radical. So, and then the peroxy radical is again very reactive with NO. So the another NO just steals another NO2. And then finally, we're left with the OH. And then, if you look at these two reactions here, we've done our conversion from NO to NO2. Recall that NO2 will react with sunlight to form NO again, but then producing ozone as a byproduct, in effect. What we've done here, though, if we take all of these reactions and then we kind of condense it to this one line here, and look at all the things going in at one end and all the things going out the other end, this is what we get. So we have our methane here going in. Now, by the end of this whole process, the methane is completely chewed up. So this is an example of where OH-initiated chemistry is removing a VOC from the atmosphere. Oxygen's going in at one end. We've got NO going in at one end, and then of course we have our OH, which is kind of stimulating the whole process. And then out the other end, got some formaldehyde, that can go on to do its thing. But then out the other end we've also got our two NOs, our water, the OH radical, and ozone. What's happened here is that the amount of the amount of OH going in is the same as the amount of OH coming out. That's been recycled. The amount of NO going in one end is the same as the NO going out the other side. But what we have added is an ozone molecule. So through this process of VOCs being decomposed in the presence of NOx, this is actually an effective way of making ozone. So if you have both NOx and ozone in the same place, NOx and VOCs in the same place, which is normal for a polluted environment, vehicles emit NOx, vehicles emit VOCs, then you start setting this reaction up. This is why, this generalized reaction is why you get ozone being produced in polluted environments. And then you can kind of summarize it with this kind of cycle here. It's a bit complicated, but this is showing that where you get these pollutants in one end, so now again, using methane as an example, but you could put most VOCs in there instead, is we have this process by which we are initiating all this chemistry. So with our OH radicals and our peroxy radicals, what these are doing is chewing up all these VOCs and CO and so on. And this is producing our CO2 and going through here formaldehyde, which can ultimately be oxidized to CO and then eventually CO2. The end point of all our VOCs through oxidation is going to be CO2, water as a byproduct. But in the process of going around all this cycle, we are producing all of this ozone as a byproduct. And that is just because we have this NOx cycling going around here, our conversion between NO and NO2, and every time the NO2 gets converted back to NO, it produces an ozone as a byproduct. Well, that's not the only place where this oxidation chemistry plays a role, because there is a kind of like a limiting factor to it, which is our hydroxyl radical will also react with our NOx as well. And then this is the kind of like the end point of our nitrogen chemistry. So much like sulfur cycle, the kind of end point in the atmospheric chemistry bit is where you convert it to nitric acid. So this is its fully oxidized form. It is not as chemically active when it gets to this form, at least not in the gas phase. And all this is simply nitrogen dioxide plus a hydroxyl radical. So if we've been making all these hydroxyl radicals and we've got all this nitrogen dioxide present, then we will start to make nitric acid. Typically, in a polluted environment, time scale of this reaction, we're talking kind of about minutes to hours to start producing the nitric acid. Obviously depends on the concentrations you have and so on. Now, this is not the only process. There are lots of other specific compounds that can be made using this complex chemistry. So when you have nitrogen reacting with these organic molecules, you can form these things, organic nitrates and so on. And there are some very exotic molecules. I'm not going to go into great detail about all of these. Just know that they're out there. It's not quite this simple. But if you had to pick one route, one sink for the NOx reservoir, this would be considered the major one. Okay, so that was a very quick tour of some very complex atmospheric chemistry there. I'll just stop there. Does that kind of make sense to people so far? Or is there anything you'd like to ask about that? No? Is everyone more or less happy with this one? Okay, because I'm just about to make it even slightly more complicated, and that's what happens when you take the light away. Now, this is kind of like an extension to some of the other chemistry that I've already talked about. Things can also get complicated at night. That's because you have this extra thing in play called the nitrate radical. That's NO3. Now, I'd just like to stress, right, nitrate radical, NO3, that is not to be confused with nitrate that forms salts or goes into solution. The difference between the nitrate radical here, NO3, is the fact that it doesn't have a negative electric charge to it. This is a neutral molecule and it forms a radical, so it's very reactive. But it's also not very stable in sunlight. So if you take your nitrogen dioxide, react that with ozone, this will make your nitrate radical here. But then the instant it comes in contact with sunlight, it immediately falls apart again to form nitrogen dioxide, and it releases the spare oxygen, which can then go on to combine with oxygen molecule and form ozone again. So the process just goes straight back again. So in daylight, you don't tend to think of nitrate radicals as being very significant. But at night, all of a sudden, you stop this reaction occurring, and then you can start to build up nitrate radicals in the gas phase when you have ozone and nitrogen dioxide present. Reason this is important, two reasons. First of all, nitrate radicals are very good at attacking carbon-carbon double bonds. So if there's any molecule that has a carbon-carbon double bond in it, it's a very strong sink of that molecule. Now this is especially important for some of the biogenic VOCs that I mentioned about in the carbon cycle lecture. So certain VOCs, some VOCs, not all, react very quickly to them. Also some of the sulfur compounds that I talked about last week, so your dimethyl sulfide for instance, that will react very quickly with nitrate radicals. This was mentioned in the previous lecture. The other reason this is important is there's also this process here where in the presence of water, so if you have a cloud or if there's a haze with enough water content in it, you can also form nitric acid from nitrate radicals. So this is combining with another nitrogen dioxide to make this horrendous molecule here, N2O5, but as soon as that gets into contact with water, it will form two nitric acid molecules. So this is a sink. So these radicals can act as a sink for NOx at night, forming nitric acid. So this is important because normally the previous reaction I showed, OH, you need sunlight to form OH. OH radicals do not normally exist at night. But nitrate radicals, on the other hand, do. Ozone can exist at night, and nitrate radicals exclusively exist at night. And they're an important sink, as I said, certain VOCs, but they're also an important sink of nitrate itself. So what this is basically saying is the nitrate chemistry doesn't go to bed at night, it just changes its form. So what's the end product? I like to pick this out as an example. Don't know if you'd recognise these. Both these satellite images are from NASA. Don't know if you recognise the geography. This here is the Po Valley in northern Italy. And this here is the San Joaquin Valley in California, over in America. Now these two locations have got something in common. First of all, you can see this big white haze over both these regions here. That is not a cloud. That is a pollution haze. That is all particulate matter that you see. This is an example of where the formation of particulates can change the atmospheric albedo. You create this thick regional haze that will reflect sunlight back up to space. The specific thing that both of these areas have got in common, though, for starters, they're both these kind of valleys that are very good at kind of containing pollution. But also, both of these areas have these big both of these regions have big industrialized areas, creating a lot of pollution. So, in the case of the Po Valley in Italy, you have Milan up here, and in the case of the San Joaquin Valley, you have the San Francisco Bay Area conurbation up here, which has got big areas like San Francisco, Oakland, and so on. And then what happens is you're creating all this NOx pollution. But then it goes downwind, and then you get into an area where there's a lot of agriculture. So this area in northern Italy here, the Po Valley, and also the San Joaquin Valley there, you get a lot of cultivation, in particular dairy, beef, cattle, but also other forms of agriculture as well, where we are all releasing this excess ammonia to the atmosphere. So you've got this great mixture here where we're making all this nitric acid. This is from our NOx, mixing it with our ammonium. That makes ammonium nitrate, and ammonium nitrate will form a particulate. and that will, in some areas, that can be a huge contribution to PM2.5. A lot of areas see this, there's a lot of areas where this is seen as like one of the big contributors to particulate pollution. So people have been spending a lot of time and effort trying to get NOx emissions down. But it's also true that if you were to get rid of the ammonia emissions, then then you would also, that would also help to reduce the amount of ammonium nitrate being formed. Also the ammonium sulfate as well. As a result, there's certain areas of the world, the ones I picked out here, California, Holland and Denmark, they have already made efforts to try and reduce the amount of ammonia being released from farms by changing farming practices and so on. They are trying to introduce that in the UK right now. So that's kind of like in a very hand-wavy way what's going on, but going on to some actual chemistry. This is kind of generally the process that we're talking about. It's not that complicated. So ammonia plus nitric acid is makes ammonium nitrate. The bit that's slightly complicated about the ammonium nitrate is, unlike ammonium sulfate, you can actually split the ammonium and the nitric acid back apart again. So if you heat it up, it will go back to being ammonia and nitric acid. And of course, ammonia will also form salts with other acids. So the examples I picked out here, ammonium sulfate, that was talked about last week. So if you make some sulfuric acid, you can make ammonium bisulfate or ammonium sulfate. And also another one that I picked out here, ammonium chloride. If you've got a lot of ammonia and you've got some hydrogen chloride in the gas phase, then you can form this ammonium chloride as well. Not generally thought to have been a major source of pollution, this, but it's just recently coming to light that this is really important in certain areas, in particular India. As a result of all of these, what it means is that whilst ammonia is released into the atmosphere as a gas, most of the reduced nitrogen in the atmosphere is probably going to end up in the particle phase. That's not to say ammonia isn't a big source of pollution, and it can cause problems immediately downwind of a source, but most of the time when we're talking about reduced nitrogen in the atmosphere, we're talking about ammonium in the particle phase. And then, like most particles, one of the main loss mechanisms is through wet deposition, so being rained out, much like the sulfur. And when it rains out, what happens goes straight back into the hydrosphere or into the pedosphere, and then made available for the biosphere again. It's a few more complicated things as always. Nitric acid. It's not as strong an acid as sulfate. So, as discussed in the sulfur cycle, sulfuric acid will kick nitric acid out of particles, but also nitric acid can kick hydrochloric acid out of particles. So it's like a kind of a hierarchy where the strongest acid is sulfuric acid, followed by nitric, followed by hydrochloric. This example here, so if we have some nitric acid in the gas phase, that's been produced from some pollution, say, we have sodium chloride, that could be a sea salt particle, so formed from sea spray. Then the nitric acid will react with that to form sodium nitrate, and then kicking out hydrochloric acid in the process. Then another example would be a mineral dust particle. So if you've got some mineral dust that has calcium carbonate present, the nitrate will kick that out in the form of carbon dioxide. So nitric acid, whilst it might not necessarily, it can get kicked out of particles by sulfuric acid, it will find a home for itself on these types of particles. One caveat here though is that these particles, your sea spray particles and your dust particles, these ones tend to be a bit larger. So basically the nitric acid will attach itself to a large particle which will fall out of the atmosphere a lot easier. So that gets lost through dry deposition rather than wet deposition. But if it can't find anything to condense onto, it will just happily sit around in the gas phase and eventually find some other surface to stick to. So be it a body of water or a building or the ground or something like that. And of course, when it then deposits, nitric acid, as I said, very soluble, very easily get back into the hydrosphere stroke pedosphere. Okay, so just to summarise, I think I'm doing a little better for time than I was expecting. We've got our emissions. So I've categorised our emissions into two groups. The ammonia, that's mainly from farming practices. The NOx, mainly from combustion. Although there are certain exceptions. If you've got over-fertilised land, as I said before, that's a source of NO. So we have our NOx emission to the atmosphere, and then with sunlight and that whole bunch of slides earlier, just kind of very glibly condense that into chemistry. And then that gives us our gases, ammonia and nitric acid here. So the ways out of the atmosphere, first of all, we've got our dry deposition, so our ammonia and nitric acid, that can just stick to a surface. The nitric acid can attach to coarse aerosol. By coarse, I mean bigger than a micron. So that's forming our sodium nitrate or calcium nitrate, again, lost through dry deposition. Well, then we have all these processes here where we can get into fine aerosol and get into clouds. But then, of course, cloud droplets can dry out, so they can form aerosols again. Well, they can also go back to gases. So we can get these interchanges between ammonium nitrate and ammonia and nitric acid going on here. But ultimately, if it gets into a cloud, one of the main loss mechanisms is our wet deposition. So all of this atmospheric NOx, all this atmospheric nitrogen that we're releasing, ultimately it will find its way back down again. So then you've got to ask yourself so far I've really just talked about the effects of putting all this nitrogen in the system. What I've not talked about is what the effects of this are in the Earth system. What we can see is, I mean, if you put things in the atmosphere, it's ultimately going to end up in hydrosphere stroke pedosphere. If they're going at the pedosphere, leaches out, again, ultimately goes into the hydrosphere. One of the endpoints for all this extra nitrogen is going to be in rivers. It's a similar case with the phosphorus cycle as well, as we'll be discussing more about that next week. So one of the things that has been noted is this huge increase in nitrogen in these rivers. Part of this is because we've been depositing all this extra nitrogen. This is again going back to this Galloway paper. So we have this map of the world. This is estimating how much nitrogen is depositing from the atmosphere onto the surface of the Earth. Well, it will ultimately go into the pedosphere or the hydrosphere. And you can see we've got a big change between 1860 and 1993 here. Thing to draw your attention to is all of these hotspots here. This is basically where you have all your big pollution centres, all your industries. This is where all the NOx is being emitted. Also where you've got lots of agriculture or lots of biomass burning as well. That's where you're emitting your nitrogen to the atmosphere. And with the exception of nitrous oxide, what goes up must come down. And it's all kind of, because the atmospheric lifetime, we're more talking days rather than weeks, years or anything like that. It tends to get kind of deposited quite locally. And it's not just because human activity has increased. A lot of the increase in the amount of nitrogen, being produced, is partly because of the very nature of how we're doing things. So you compare the mid-19th century with the late 20th century, and you're comparing practices. Grain production, okay, or any other staple for that matter. We've moved over to a much more intensive agricultural model, but we've increased the amount of artificial nitrogen fixation, as I was talking about earlier. So rather than going for biological nitrogen fixation, manuring, that kind of thing, we're now reliant on Haber-Bosch. So we're producing a lot more we're putting a lot more nitrogen into this system, but there's also a tendency to over-fertilise soils as well. So we get the more emissions through the leaky pipe model that I talked about earlier. Meat production, and I suppose technically this should include dairy as well. Again, it's a move to more intensive farming. And as well as just increasing the overall volume of activity, so you're increasing the number of cows produced, again, the cows are being close together, you're getting more more urine in contact with feces, that is producing more ammonium. And then energy production. So the example there is going from wood to coal. Coal is a higher temperature combustion, and it produces more NOx per unit energy. Okay, so that is also a reason why the NOx emissions have gone up. As well as the coal burning, you can also add to that oil burning as well. That is also a very strong NOx emitter, again, because the combustion's at a higher temperature and pressure in the case of internal combustion engines. So, change all these activities. And then this is another reservoir diagram, and this is just referring to the different chemical reservoirs. So this is your kind of pre-anthropogenic diagram here, and then this is our post-anthropogenic diagram. What we can see here is that this isn't some kind of tiny little tweak to the fluxes in this system. This one is absolutely huge. So we have our natural nitrogen fixation, so, you know, and you'll really have to excuse me, the units are missing on this plot, which is completely inexcusable. So we've got our 5 gigatons a year through our lightning action, 98 through natural nitrogen fixation, and then in the kind of pre-industrial period we've got 7 through our biological nitrogen fixation. Move to the industrial period, all of a sudden this arrow here has gone huge. That is Haber-Bosch in action. So that is producing all of this fixed nitrogen here. And then as a result, and also we have our nitrogen from the atmosphere going via the fossil fuel burning. That one's got much bigger as well. And increased amount of biomass burning, wildfires, agricultural burning, etc. That one's also increased a bit, not quite as dramatically though. But then we increase all these other, so if we increase these fluxes from our primary reservoir, that's our molecular nitrogen. So we've got all this extra reactive nitrogen, and then all the other fluxes out of that increase as well. So we have more fluxes of NOY. I perhaps should have clarified actually, I think I missed this off a slide. NOY is basically the sum of all reactive nitrogen. So that is NOx plus nitric acid plus any other forms as well. So reactive oxides of nitrogen, I should say. And then we have our increased ammonia emissions as well. That's from our agriculture. And then all of this has got to go somewhere. So some of it can go back into the biosphere, but some of it goes into the aquatic environment. And you can see here what the fluxes have gone here from 5 to 20 and 12 to 14. That is going to increase the burden in the aquatic environment. So just a quick kind of comparison. Teragrams nitrogen per year, 44. 82% of that is anthropogenic. The ammonium, 72% is anthropogenic. And by that anthropogenic, I mean pre-industrial compared to modern. Now, just to put this in context, if you recall our carbon cycle lecture, the carbon cycle, what's happening there is where we've made a relatively small perturbation to some fluxes in the carbon cycle, but that is, because of the long lifetimes, that is building up and up and up gradually in the Earth system. The sulfur cycle, as I described last week, that is one where the anthropogenic fluxes are kind of comparable in magnitude to the natural ones. So it's a big change, but it's kind of, it's not making a dramatic alteration to the reservoirs. Nitrogen, on the other hand, the anthropogenic perturbation to that is huge. Now, this is partly because there is so much artificial nitrogen fixation and NOx pollution going on, but it is also because reactive nitrogen persists in the Earth system. So, we're fertilising land. Is that a good thing? Can be a good thing. Also be a not so good thing. Now, I'm going to talk a bit more next week in the phosphorus cycle lecture about eutrophication, because as we'll see, the phosphorus and nitrogen are quite similar in this regard. But there are many biological systems that are nitrogen limited, as I was saying in the biosphere lecture. So you put more nitrogen in the system, you are going to increase the amount of production. But it's not necessarily going to be the production of the things you want. So sources of excess nitrogen, atmospheric deposition, talked about that. So if you have atmospheric NOx pollution, that deposits to the ground, that's going to create excess nitrogen. Direct runoff. So if you over-fertilise land, the nitrate dissolves, and then that'll go through the groundwater into rivers. Also, any effluent not going where you want it to. So effluent from cattle farming stuff, that gets into rivers. That'll increase your nitrogen load. So what's the problem with that? Well, all of a sudden you change a ecosystem from being nitrate limited to not nitrogen limited. That can mean you can get a lot of organisms you don't want, and that can significantly alter an ecosystem. Also, if you're increasing the amount of nitrate in a system, that will increase acidity. Now, you can get increased acidity from acid rain, but you can also get it through nitrate. Even if the pollution is in the form of ammonium nitrate, which is pH neutral, what can happen is nitrification can kick in. These organisms will start converting your reduced nitrate to oxidized nitrate. By this, I'm referring to nitric acid. So all of a sudden, if you increase the nitrogen load in soil, that can then start becoming acidic, and then that might cause problems for organisms that don't like acidity. And then what happens with these ecosystems is you can also temporarily change the balance of an ecosystem into something you might not want. But then also, if you completely kill off some organisms, or if you introduce some more nitrate tolerant organisms, they can become established. Some of these changes can then become permanent. And on top of that, as well as these bad effects, is that I've talked about the atmosphere as a reservoir a lot, but what I've not talked about is the pedosphere as a reservoir. Now, mentioned earlier that nitrogen can bind to soils and so on, but it's also very soluble. But it can also persist for quite a long time in the groundwater. So one of these things that's only just starting to become apparent is how much nitrogen is actually stored in groundwater. We have these big reservoirs here. Now, of course, you've got a big reservoir. If you've got a big reservoir, and you kind of know the sources and sinks, then for a given sink, that's a big turnover time. So just to remind, I'm going to keep drilling this in, the turnover time, that's your burden divided by the sum of your sinks. If you've got a big turnover time, what this means is that it can install on this a kind of like a delay. So we've got all this kind of excess nitrogen in the soils, but if you've got a big groundwater reservoir, it can take its time to build up in there, and then eventually it'll start leaching out of this big groundwater reservoir and end up in rivers. So this can create a kind of like a time delay between creating excess nitrogen in the pedosphere and then seeing the excess nitrogen in rivers. And there's a paper there which I've linked. I'll put a link for that on Blackboard as well. That's a fairly recent one where they basically reckon that we've been underestimating the magnitude of this problem the whole time. So finally, I mean, that's the kind of the causes of that's the cause of the anthropogenic perturbations, kind of effects that we're looking at. Now we look to the future. What can we expect? So this is following it's a fairly old paper now, but where do we go from here? We've got all this nitrogen fixation. Are we going to carry on fixing more and more nitrogen into the future, or are we going to carry on at a steady rate, or are we going to potentially do less? One might expect if the world's population carries on going up, then we might need to fix more nitrogen just to feed the world's population. You know, you can't grow crops without fixing nitrogen. So one way of projecting this is if you just take the amount of nitrogen fixation in the current world, and then you look at the population currently, or in this case 1995, and then the projected world population in 2050, and then you just scale it by that amount. And then we get this is divided according to the continents. This is the amount of increased nitrogen fixation we might expect. If we just assume that the amount of nitrogen fixation per capita is maintained. Oops. However, the world's population is not just increasing. People are consuming more. So we've not just got more mouths to feed, but the mouths we're feeding are eating more and are also eating foods that require more nitrogen fixation. So, for example, as people begin to eat more meat, you're not just having all the you're not just getting all this fixed nitrogen in the form of the animals that we're eating, but of course you need to fix the nitrogen to grow the crops to feed these animals as well. Overall, you are still fixing more nitrogen in the process of feeding people. Now you can see here for North America and Europe, you know, what we'd like, Australia as well for that matter, what we'd like to call the more developed world. The increase is, you know, a relatively modest doubling in the case of Europe. But then we go to Asia, Africa, South America. If we then kind of project the nitrogen fixation footprint as well as the population increase, we just assume that everyone is going to be wanting to have the same amount of nitrogen fixation as your average North American does nowadays, then we're looking at some huge increases in nitrogen fixation. And then this kind of creates a problem, because all of this nitrogen, when you fix it, has to go somewhere. So we're fixing all this nitrogen. Most of it in the modern world fixed using Haber-Bosch artificial nitrogen fixation. Of course, some of it, you know, we can still fix biologically, but it doesn't actually matter which one you use, Haber-Bosch or biological nitrogen fixation. Really, all we're doing is creating this reactive nitrogen. So grow some crops with it, and then also grow some livestock with those crops. And then that's when all these byproducts start. So to recap some of the previous lectures, we've got our nitrous oxide here, that's greenhouse gas, bad news obviously. We're also producing nitrogen oxides. Recall that the leaky pipe produces NO, but also the act of cultivation and so on, that involves burning fuels and so on. That will produce NOx as well. We're putting ammonia in the gas phase, and nitrate will get leached out. And then, of course, the livestock farming. This will also produce all of these. So that is also putting all these in the atmosphere and in the hydrosphere. And then where does it go? So in the atmospheric ones, with the exception of the nitrous oxide, that's got to come down, end up in that eventually, through wet and dry deposition, ends up in our ecosystems, in our rivers, and the leached nitrate as well, all ends up in our stream waters, so in rivers, groundwater, etc. What this is saying is that all of this, with the exception of the nitrous oxide, all this nitrate, all this nitrogen is going to end up somewhere, and ultimately it's all going to end up in places like rivers where it can potentially cause bad things to happen. if you try and sorry, I should also point out emissions of NOx and N2O from here as well. If you try to mitigate this, so if you're trying to look to the future and you say, well, we're going to have to look at increased nitrogen fixation just to support a growing world population. So then what do? I talked about earlier about ammonia abatement. So, you know, if you can look at something, well, is there any way we can stop this ammonia being emitted? Is there any way we can stop this nitrogen oxides being emitted? If the nitrogen has already been fixed and we just stop the release from one part of the system, it's still staying there in the form of reactive nitrogen and it still has to go somewhere. So what you potentially risk doing, so for instance, if you change your farming practices so you don't release as much ammonia to the gas phase, what could happen? So if you, for instance, if you're able to stop it being released in the form of gaseous ammonia, it can end up in the soil, it can become nitrified and then it becomes leached out, or it can be emitted in the form of nitrogen oxides, but it still all ends up somewhere in the system. So we've got to ask ourselves what strategies can we apply? And one of the obvious ones is to actually reduce the amount of fixed nitrogen that we're using in the first place. So, with that, I'm just going to go on to a couple of summary slides. So this is just basically summarising the major processes that we need to worry about this is the kind of wider Earth system. So I've got our atmospheric processes up here with our ammonium and nitrate, which takes our NOx and our ammonia. This is through the nitric acid. We've got our biosphere, pedosphere and hydrosphere. I've just lumped these all together for the purposes of this diagram. Well then, to highlight the key bits that the human activity modifies is these arrows here in red. So the big ones we've got fertilizer manufacture and combustion. So we have our fossil fuel burning and the conversion of N2 to reactive nitrogen. And then what we're effectively doing is putting that in the biosphere, but I've just put this big red box there that just says over-fertilised. So that is increasing our burdens, increasing our fluxes. But it's these two processes which are the major ones. And to summarise the effects of these, we have our NOx emissions. So human activity produces NO from combustion, and which we collectively call NOx because of the interchange between NO and NO2. Because of enhanced biological processes, we have ammonia, NOx and nitrous oxide being produced, byproducts of farming. As a pollutant, nitrogen dioxide is toxic, but the other big effect of NOx emissions is they increase, in combination with VOCs, they increase ozone concentrations. Now, one thing I've not stressed yet, ozone in itself is considered a pollutant in the troposphere, but it's what we call a secondary pollutant. We don't directly emit it to the atmosphere. It's produced as a secondary product of VOCs and NOx. But as far as pollutants go, ozone is a really bad one. It's toxic, so it's harmful to human health. It's a greenhouse gas, and it also damages plants as well. So inhibits net primary productivity, also suppresses crop yields as well. So generally speaking, ozone in the troposphere is very bad. As with sulfur, the main sink from the atmosphere is conversion to nitric acid, and these can form particulate matter. Our excess nitric acid and ammonium, these can cause acidification and eutrophication, which is the impacts on ecosystems. And finally, nitrous oxide is one of the greenhouse gases we need to worry about. So this is when we're talking about nitrogen as a pollutant and the effects that human activity has. These are the main things that we care about. So I think we're actually reasonably early. So every year I have a go at reordering the slides on this one, and it just, without taking any slides out, I managed to get it going quicker and quicker. So apologies if you're getting to leave early. So unless anyone has got any questions, should mention as well, I forgot to say earlier, I did have a question about the deadline for the assignment. Just like to remind you that it's 1 minute to midnight tomorrow, and it being electronic submission, it's strict, so it gets flagged if it's late. And also, I would like to say, I get this every time, don't leave it till the last minute to submit. Sometimes it doesn't behave perfectly well, but I have to go off the timestamp when it's submitted, so please don't leave it to the last minute. Okay? Thank you. Oh, does anyone need this? No? Right.
So in terms of quite a lot of information on this model.
Yes, it is.
In terms of revision and preparing for the exam.
Right, you're going to ask what's going to be in the exam?
No, not so much, no.
What? You can? Oh, I'll have to turn it back on again. There you go.
In terms of going through, what's the word when something's more important? Prioritising.
Right.
Prioritising.
What I will say,
Yeah.
in terms of prioritising, any slide that says key concept on it, pay attention to that.
Yeah.
Any slide that says summary,
Yeah.
I would pay attention to that. They generally indicate the more important stuff. What I would stress though is the essay questions. Basically, what gets you 100% on the essay questions is basically knowing everything relevant. Okay? Now, people don't generally get 100%.
Yeah.
But the important thing with the essay questions, though, is being able to demonstrate knowledge that's relevant to the question. Okay. Now, if you want to get an idea for the types of questions, dig up the Now, I can't dish out model answers today.
No.
That's, again, but to be honest, model answers don't exist because they're actually scored using a rubric. But the idea is you are presented with a topic, and then you are basically supposed, and it's normally a very pithy question, you'll see this in the past papers, and then you are kind of basically required to discuss everything that's of relevance to that. Okay. The more you know, the more relevant it is. So it can be a bit kind of encyclopedic, but it's a case of focusing on what's relevant, and as I say, key concept and summary slides, they're the more important ones. Generally speaking, when it comes to detailed chemical reactions and things like that, that's the kind of thing you could in theory get marks for, but only if it's kind of really relevant.
If it is relevant, yeah.
I'm not going to discourage you from having a good knowledge of the chemistry. All I'll say is that it's not necessarily required to get the high marks, it's having a completely in-depth knowledge of the chemistry, say. But obviously I can't preempt what's going to be in this year's exam.
Yeah.
That's mainly because I wrote it ages ago and I can't actually remember that. That's absolutely true. And I will be going through this I'll be going through this again on the revision lecture.
Yeah.
I would suggest in the meantime, if you want to get a flavour for it, I would look at the past ones. The other thing, and I meant to say this earlier, so it's something else I meant to say. Next week, phosphorus cycle lecture, but only half of it will be phosphorus, the rest will be exercises on calculations. So there'll be more of those next week. Meant to say that earlier, do apologise, forgot. So we will be going through more of the calculation stuff next week. Okay. Calculation stuff, what I would say on there is really, really pay attention to the slides that say key concept.
Yeah, okay.
Because the actual maths itself, the equations are relatively straightforward, but I may require you to remember what those equations are. They're really important ones, you know what I'm saying?
Right.
So,
a key concept equation, learn it.
If it says key concept, it's a good idea to remember it. And the really common ones, like definition of turnover time, make no secret that that's an important one to remember. Things like that, you know.
Right.
As for that, right, so really it's the other thing as well, and I did stress this at the start, is the exam questions another key thing is staying to topic as well. Yeah. So you've got to be able to take your knowledge and apply it to the question.
Yeah,
I should
no
have mentioned.
going off topic.
Well, you can if you want, but you just won't get marks for it.
Yeah.
That's no. I mean, seriously, I've had exam scripts where there've been entire pages that have scored 0,
Yeah.
and someone just started writing and went off topic, and it was just like. So yeah.
Yeah. All right. Well, thank
Anyway.
you. Cheers for that.
Yeah.
I wanted to ask about the
Leaky pipe model. Yes.
When you get the leaks, does that mean that the reservoir itself is decreased and it ultimately will be decreased?
Yes. Now, that's a good question. Yes, it does, but it's yes, it does, but not by the fraction of nitrogen that ends up getting leaked out is actually relatively small. So the amount of when you have over fertilised land, the majority of the nitrogen will actually end up in the biosphere, leached out, or kind of nitrified, denitrified. It's a small fraction gets produced as NO or N2O as a byproduct. That's a damn good question though, because I don't have those numbers to hand.
Okay. That's fine.
Certainly not off the top of my head,
Okay.
but it's a minor fraction that does that. But yes, you are right, it does reduce the burden ever so slightly.
Okay, thank you. Thank you.
Yeah.
One question I want to ask about this question is Q is constant with him or will change with him?
Hang on. Q is the flux. Yeah. So, if the burden is changing and K is constant, if the burden is, hang on, let me get this one right. For a first order system, let me just get that. Right. Oh, God. So I'm forgetting my. There. For the first order system, so this will be Q, the sink. So if that S is Q in the other thing. If M is changing and K is a constant, then what does that make? Does that mean that Q is changing or constant?
Changing.
Exactly. So if the burden is changing for a first order system, then Q will also have to be changing. That is because of the first order nature of it.
So you can also calculate Q by Km?
Well, yeah, that's, go back to this slide here.
It's the same to the sink?
I mean, this is the, there we go. Yeah, but, well, no, it's this equation here. So if you ignore the gamma there, so this is just the generalised form. So if you've got first order sink, so gamma is 1, so S equals Km. If you know one of these, sorry, if you know two of these, then you can calculate the other. So it's much like turnover. So if you know the burden and you know the K, you can calculate the sink. But if you know the sink and the K value, you can calculate the burden. Does that make sense?
Yeah, so how about Q value, the source?
Well, sources are ever so slightly different because that equation there with the K value, that applies to sinks,
Yes.
right? Now, if you apply it as a source just goes into a reservoir. It doesn't care what the burden is of the reservoir it's going into. It just goes in there. Okay? All right.
Is the class still going on?
Not really. We're just dealing with questions. Do you need to use this room?
I have my USB stick.
Oh no, you go right ahead. Won't be the first.
Yeah.
Cheers. So if you have a source, that will just add to a burden, and it won't make doesn't care what the burden is, it will just keep adding to it. Okay? So the source does not depend on the burden it is going to. Okay? If it's a first order sink, then it depends on the burden it is coming from. Does that make sense?
Yes, but here Q means the source.
Yes.